Brownian motion. This happens when a particle is immersed in a medium, in a fluid made up of molecules. The particle is, say, the size of, say, 1 micron, 10 to the minus 4 centimeter. And the molecules are typically of size an angstrom, 10 to the minus 8 centimeters. So this is 10,000 times bigger than one of the molecules, yet that's not much bigger. So that the number of molecules hitting this on one side doesn't quite balance on the other side, so this kind of moves in a random way. And one observes this motion at fixed time intervals, say every 10 seconds and so forth. So if you observe this at every 10 seconds, say at point A, you observe it, so it would go like this, and it will go like this, and it will go like this, and it will go like this at point B. So this is tau is 10 seconds, say. Every 10 seconds you observe. It makes a rather irregular path. However, if you observe this for 1 second, then between these 2 points, then between here and you make 10 observations, then it would look like this. Each one is 1 second. Tau is 1 second. If you take this and observe it for 0.1 second, so there are 10 observations, it also looks like this. Tau is 0.1 second. So it's self-similar. It looks the same when you decrease tau. And this is so all the way until tau reaches the molecular cutoff, molecular time, which is of the order of 10 to the minus 20th second. Then after that, it doesn't change. But before that time, it's self-similar. It's a fractal. The path is a fractal. And the definition of a fractal is that it's a dimensionality of dimension d. And this d is determined by, say, you measure the length between A and B. Length is the L is the length, the measured length of the path between A and B. And tau is the step size. So the length is, you see, if you measure it at 10 seconds, you would add up all these paths. If you measure it at 1 second, you would have more paths. So the length is different. And L is proportional to tau, and this exponent is defined as 1 minus A, and D is defined by this. D is the fractal dimension. If you have a smooth curve, then if it's a smooth curve, then it doesn't matter how you cut it. You always measure the same length between A and B. Then the length is independent of tau, so D is equal to 1 if it's smooth. But here it's not smooth, because when you decrease the step size, the path increases, and that's typical of a fractal. And for Brownian motion, D is equal to 2. The fractal dimension is 2. That is, this path almost covers, also it's like an area. It generates an area. You can generate. I'm sure you know how to. You've seen it. You can generate the fractals by construction of fractals. For example, you take this, so A and B, and the next time you take this, and the next time, if for every length you do the same thing, so you do this, and so forth, and then you generate a fractal. And depending on your step size, the length you measure is different. So if you measure the length tau, in our case you would get a line of slope equal to 2. The slope is d. The slope is equal to 1 minus d. But of course, you measure until you reach the molecular cutoff, then it goes to 0. And this is the molecular cutoff. And we're talking about this region, which is a long stretch because the molecular time is 10 to the minus 22nd. So in macroscopic time, it's a fractal. How do you treat this? How do you describe it? It's not something that we have encountered before because the position of this particle is not definite. It varies randomly. Einstein proposed a classic model. It's one-dimensional random walk. And Einstein realized that the essence of this is that if you choose any tau, the distance between A and B is a sum of a large number of random steps. So particle at x and t. X is a sum of large number of random steps. In modern, Einstein first realized this is the most important point. In modern language, we would say that x is a sum of a large number of stochastic variables. Stochastic variables. And this has been treated in a probabilistic way. So you just set this line x. X makes a transition from this point x to x plus delta. And this transition has a certain probability. So the probability of transition x to x plus delta is equal to f of delta times d delta tau. Tau is the time interval in which this happens. Time tau. So this f then is postulated as a probability. It describes the system. It has the property that f tau of delta should be equal to minus f tau of minus delta because the left right should be symmetrical. And since it's the probability, integral d delta f delta is equal to 1. So this is the basic postulate that there's a probability. And the important thing is this probability only depends on the position of x. It does not depend on the previous step. There's no memory. That's the essential thing. And now we call this a Markov process. of earlier steps. So now you can ask, what is the time rate of change? Is x. I'm going to have dx. The number of particles in dx at time t would be equal to some density n of x and t times dx, where n is the density. And the number of particles in the dx at time t plus tau would be equal to n of x t plus tau dx. And how does this get increased? It increases because, say, this is x plus delta. This is x. This is at x plus delta. Particles from x goes in here. And also, it could go here, and the delta could be positive or negative, so particles could go from all other places into this interval in time interval tau. That's a statement. And now the number of particles is conserved. And therefore, the conservation of particles tells you that n of x t plus tau times dx, the number of particles in here after time tau, must be equal to the transition from all other places. And that is equal to integral d delta from minus infinity plus infinity of n of x plus delta t times the probability f tau of minus delta. This is the total number of particles that leaves delta and go into x. And so this, what leaves this one must go into the increase of the particles in n's. So this is the crucial equation. This is the equation that Einstein wrote down. This is the basis of the model. It's the conservation of particles, which is very reasonable. Now suppose we now let tau go to 0. Let tau and delta both go to 0. Very small. Let tau go to 0 and delta go to 0. Then I just expand the equation in a Taylor series in delta and tau. Then I would get, for example, I would get n of x and t plus tau d n x of t dt, that is the left-hand side, plus higher terms would be equal to integral d delta minus infinity plus infinity, f t of delta, because delta is ft, I can change minus f to delta, so I can write it this way. And here, I just expand the bracket in a Taylor series. I get n of x and t plus delta dn xt dx plus delta squared over 2 second derivative n xt dx squared plus higher terms, which will go to 0 when I take the limit. Now, the first term, this is independent of delta, so it comes out, and this integral is 1. Therefore, this is equal to, the first term is 1. It's just n of x and t. This is the first term. The second term is 0, because You integrate f delta with delta, and f is symmetric in delta. This is asymmetric, so it's 0. So all I have is this term, integral d delta minus 1 plus infinity delta squared times f tau of delta 1/2. It's this thing times d2n of x and t dt. I just remind you, this is so because theta f is equal to 1. And this is, and the second term is 0 because integral d delta f is equal to 0. So I'm left with this n and this term. And of course, this n cancels that. So you get an equation. The equation is dn of xt dt is equal to some constant d times second derivative xt divided by x squared, where d is 1 over 2 tau integral d delta, this is squared here, yeah, f of tau delta. And this is a diffusion equation. And this is a diffusion coefficient. And therefore, the solution to this problem is the diffusion equation. And you can solve this equation immediately because it's linear. And the solution is n of x and t is equal to 1 over 4 pi dt times e to the minus x squared divided by 4 dt. It's Gaussian. And the width increases with the time. And this is how diffusion works, right? You notice that this has the property that integral dx from minus 1 plus infinity n of x and t is equal to 1. This is the number of particles. If you have n particles, it's raised by n. And this determines this coefficient in front. And n of xt, when t approaches 0, approaches delta function. And the density is just delta function at equal to 0. So if you have n particles, you just multiply by n. And in 3D, you just take this, you just multiply it by x, y, and z. So in 3D, n of x position t would be equal to 1 over 4 pi dt to the 3/2 power times e to the minus x squared divided by 4 dt. So this is a probability when you have one particle. If you have n particles, you have a density, and it will look like this. At t equal to 0, you have n particles, all located at this point. As time goes on, it diffuses out. And the width, which is the radius of this, r, goes down like 1, increases like square root of t. So when you have n particles, as time goes, it spreads out. And the radius goes out like the square root of t. And this is how particles behave, say, in the air. If you have particles in As you release it, they perform Brownian motion because of the air molecules, and it diffuses out. This way it happens if somebody opens a bottle of perfume, the scent will diffuse out. And you see that this is very simple. And the basis is the conservation of particles. And you notice that the result is independent of the detailed form of the probability F. It only depends on D, a certain constant that you can take from experiments. It is independent of the probability F in detailed form. And this is upon further analysis, one can show that this is a property of Markov processes, that because we say that this process has no memory. And the fact that the sum of a large number of stochastic variables obeys the Gaussian distribution. It's a very general result, which is proved here in a special case, and this is called the central limit theorem. This theorem accounts for the fact why the Gaussian distribution is so common in statistics. You want to measure distribution of people's ages in society. It's a Gaussian distribution. You want to measure the distribution of grades in the exam. It's a Gaussian distribution. That's because these things has a randomness, and it only depends. It has no memory of the past. And if you have memory of the past, then it deviates from a Gaussian distribution, and then we cannot describe it in such a general way. And that nowadays will be called complexity. Einstein was the first in physics to derive the diffusion equation. But it turns out that he was not the first in the whole world, because a mathematician derived this for the stock market earlier. His name was Brownian. He was a student of Poincaré. He applied the theory of random walk to the stock market. And Einstein went on to derive some important results, which gave him the Nobel Prize. He got a Nobel Prize for this and for the photoelectric effect, not for relativity. But this was all done in 1905. One of the three papers in 1905. This paper, the paper on the photoelectric effect and special relativity. This was such an important thing then, because at that time a large number of people did not believe that atoms exist. And Einstein's work showed that they exist because of these developments. First is something called Einstein's relation. Suppose J be the particle current density. These Brownian particles are immersed in this fluid, and consider a large number of them. They don't interact with each other, but they flow. So they have a certain current. Let J be the current particle current density. Then, since the number of particles is conserved, it must obey the continuity equation. This just says that the number of particles is conserved. If we now use this from the diffusion equation, we get delta J plus D times Laplacian of n equal to 0. Or the divergence of J plus d times gradient of n is equal to 0. And the solution is j is then equal to minus d times the gradient of n. This is the diffusion current. It is proportional to the gradient of n, and the proportional constant is the diffusion coefficient. Whenever there's an imbalance in density, you get a current. This is what this is. And this is the meaning of the diffusion coefficient. Now suppose there is a, now consider a vessel with a Brownian particle here, with Brownian particles, and then from Brownian motion here, in this vessel, because they don't interact. And they're under gravity. So there's an external force acting on these particles that drag them down. External force. F is equal to, say, minus gradient U. Conservative force. And then experimentally, there will be a terminal velocity. If there's no medium, this thing will accelerate. But since there's a medium, there's a dissipation, there's a friction that will oppose it. And the particle will approach a terminal velocity. The terminal velocity is such that defined as eta times f, where eta is the mobility. This is the definition. So if you consider these Brownian particles falling under gravity, they will reach a terminal velocity given by that formula, with a coefficient that is defined as the mobility. In equilibrium, however, so the drift current would be equal to the density times u. This is the drift current going down. And in equilibrium, J plus nu must be equal to 0. And therefore, minus d gradient of n plus eta u is equal to 0. However, u is equal to, but u is equal to eta times f, or u eta times gradient of u. And therefore, if I substitute it into this equation, I get minus d times gradient n minus eta n gradient of u is equal to 0. But we know that in equilibrium, the density must obey the Maxwell-Boltzmann distribution. From kinetic theory. That nx must be equal to n0 times e to the minus ux over kt. That's the Boltzmann distribution. And therefore, I can take the gradient of n, therefore minus d, the gradient of n will be minus n du over kt minus eta n gradient of u equal to 0. And when you cancel out everything, you will find that d over kt is equal to eta. And this is Einstein's relation. it relates the diffusion coefficient to the mobility. Now this is a special case of a very general theorem called the fluctuation dissipation theorem. The D diffusion is a fluctuation because it comes from the fluctuation of this particle in the medium. And eta is a dissipation. It comes from the frictional force that opposes any dragging of the particle. And these two coefficients are related. And this is called the fluctuation dissipation theorem. So it says physically that fluctuation and dissipation are different things, different sides, different views of the same phenomenon. Fluctuation says the following. You have a Brownian particle here, and there are these molecules that are hitting it. So its path fluctuates. And this fluctuation is described by the diffusion coefficient. Dissipation, however, says that you take the same particle, you would drag it with a force, and it'll encounter resistance, dissipation. And that's if it comes from the same source, comes from the same molecule. So this gives you D, this gives you eta, and these two are related. Related by KT. This is a special case of a very general statement, and I can let us just look at some other examples. So fluctuation, dissipation, voltage in a resistor, V squared average minus V average squared times beta 1 over kT is equal to 4 resistance times delta nu. This is a Nyquist theorem. He says if you have a resistor at room temperature, T, then there's generally a voltage between these two ends that fluctuates because of thermal fluctuations. And the average velocity of the voltage is 0, but the mean squared average is not 0. It's 4R times delta nu is the bandwidth out 1 over kT times this. So this is again a fluctuation. This is fluctuation. This is dissipation. Another example is what we have studied in the canonical ensemble, the energy fluctuation. We find that beta of energy squared minus E average squared is equal to T times CV. Again, fluctuation, dissipation. Another one is density in the grand canonical ensemble. Beta times n squared minus n bar squared is equal to n bar squared times the isothermal compressibility divided by V. And all these are the same type of statement as this fluctuation dissipation theorem, emphasizing that fluctuation and dissipation arise from the same source. Now, why does this show that there are atoms? Because you can show that these effects are real, and they cannot exist if there are no atoms. There are no fluctuations. And a definite demonstration of that was by Perrin, who verified all these things in 1909, who got a Nobel Prize for it. He applied all these things, he measured Avogadro's number for the first time experimentally, directly. consider a particle radius A, and you drag it through the liquid until it reaches terminal velocity. You can measure, and according to Stokes' law, the force that you need to drag this is equal to 6 pi A times the viscosity times U. If we use Einstein's relation, we will get 6 pi A nu is equal to d over kt. This is Boltzmann. And therefore, now Boltzmann's constant is equal to the gas constant divided by Avogadro's number. R is gas constant, which you can measure from an ideal gas, and A is Avogadro's number, which until that time had not been measured directly. So you plug this in, you would get A0 is equal to 6 pi A nu RT divided by D. You can measure this. You put a particle, you know A. You can measure the viscosity of the medium, and you can measure the diffusion coefficient of those particles. You plug it all in, you get A. And Perrin got A was equal to 7.05 times 10 to the 23rd. We now know that it should be 6.02 times 10 to the 23rd. Modern value. But this was the first measurement. And he got for that he got a Nobel Prize. And with this, there was no doubt that atoms exist, because you can measure Avogadro's number. And you can appreciate how all this comes about through very simple arguments. All the equations are very elementary. It's the process of thinking, it's the deduction, the power of deduction that Einstein used that led to all these things. But now you ask, what about the original work of Bachelier on the stock market? How does it apply to the stock market? Well, is there Brownian motion in the stock market? That's the question. And the theory of Brownian motion in the stock market led to these formulas. The Black-Scholes formula, which was very famous. The Black-Scholes formula gives you the predicted value of a stock or anything in the future. And the Brownian motion theory of the stock market predicts that let S of t be equal to the log of the price. PT is the price of the stock. You just take the log because that's the variable to be used. And then the probability of S, say PS, Stockmark theory would be 1 over 2 pi. They use they use sigma instead. This times e to the minus S0, some constant, minus a drift term divided by 2 sigma squared t. And sigma is called the volatility. So this is ridiculous. So it would, if you plot PS as S, it would be something like this, with a width that, with a position that drifts, with the mu t, this would drift slowly, and with a width that broadens with t. So as time goes on, you are less and less sure of the value of the stock. If you compare it with a real stock, the data would look like this. That is, the Brownian model is very good at short terms. But at larger values of S, larger deviations, it's not as accurate. That is, strange events large deviations happen more likely than you think, according to the Brownian model. That's the conclusion. And unfortunately, this stuff is very important, of course. So that is the extent we can apply the Brownian motion idea to stocks. And this tail, of course, is due to the fact that there's memory. The stock retains a memory. So now, in summary, the most important thing in this is a probabilistic treatment of the position of a Brownian particle. You don't ask what it is. You just say, what is the probability of finding it to be such and such? And then you, by very simple arguments, then you show that this distribution of x is independent of the basic probability law. It just depends on one constant, the diffusion constant, which determines the width of the Gaussian. And that's because we have assumed that there's no memory. And next, I would like to treat this in a more formal way. And I think it's a little bit early, but we'll take a break here.